So if I've got a red laser beam going through two openings, or maybe not through two openings, maybe through 1,000 openings per centimeter, doesn't really matter. We get the same interference pattern formed on a screen over on the other side. We end up getting a bright spot, dark spot, bright spot, dark spot. And by a dark spot, we mean the absence of a bright spot, right? The absence of light. Bright spot, dark spot, and so on. If this one is in the middle, right here, we're going to call this 0, and we're going to make 1, 2, and 3 on the other side, 1, 2, and 3 on the other side. We have two equations that can describe what's going on here, right? Those two equations are lambda is equal to d sine theta over n, and we have lambda is equal to xd over n times L. First of all, what do these variables mean? What does L mean in the second equation here? We don't have it labeled on here because we don't have the entire diagram drawn, but Rosie, what would L stand for? Good. Distance between the slits and the screen itself. So it would be this distance right here if we had the slits drawn there. Good. What about D? D stands for distance. Most of these things are distances of some type, right? Yeah, distance between the centers of the openings. Good. And we're probably going to be in meters in both of those. X. Jason? Yeah, distance between nodes or antinodes or node and antinode or whatever, right? And the thing we got to be careful of there is we make sure n is consistent with that. So if we make x from here to here, and we can do that, then n would be equal to what? Yep. No. 2. N would be equal to 2 in that case. If we make this x, and we can do that, right, from this point to this point, then n would be equal to what? X is the distance, right, in meters, and n would be equal to what there? Ollie? N would be 1.5 in that case. So it's okay to make x whatever is convenient as long as you make n consistent with that and make sure that you remember the 0.5s. If you're talking about a minima or a node, you're going to make it 0.5s. Good. Tell me, this second equation is valid most of the time, although it is an approximation. But it's a very good approximation the vast majority of the time. But there are situations where it's not very good. When can I use this bottom equation? Right? It's got to fit the givens, right? But we can't always use it even when it fits the givens at all. Good. If theta is less than 10 degrees, that's the hard and fast rule. At 10 degrees, the equation becomes less and less of a good approximation. Below 10 degrees, it's still good, and we can use this equation no matter what. Now, what's our rule of thumb for determining if theta is less than 10 degrees? We could calculate theta every time if we wanted to. We could say this is L, this is X. We could calculate theta and then use the top equation each time. But we don't want to do that because that means extra work. If we're going to do that, we might as well not even bother having the second equation in the first place. So what's our rule of thumb here, Ethan? Right. We want L to be greater than 10 times x. If we calculate the value of 10x, compare it to L, and if L is greater than 10 times x, then the equation is good. Okay, if it's not, then you're going to want to find the angle and then probably use this equation. All right. A couple more little things here. This spectrum that you see, or this interference pattern that you see at the top of the screen here, represents the interference pattern formed by red light. Okay. What would the interference pattern look like if we had blue light? Just blue. No, this is red light. We want to have just blue. Yep. Yep. Blue and no blue, it would look almost the same, except you would find that the blue lines would be just inside the red ones. That makes sense? And why would the blue ones be just inside the red ones? Well, remember when we were dealing with diffraction and dispersion through the prism, blue light refracted the most. Blue light diffracts the least, right? So if we have blue light, then they're going to be a little bit closer to the central maximum than red light would be, right? Violet light would be even closer to the central maximum than red light would be. What if we have multiple colors? What if we have three colors combined going through the openings and then splitting up? It's going to look like now. Well, in the middle we'd have this combination. We'll make it yellow here. The first order maximum would look like this. If we had these three colors. The second order maximum would look like this. The third order maximum like this, and so on. We'd still call this the central maximum. We'd still call this the first order maximum, the second order maximum, the third order maximum. What do you do with this? Mathematically, what do you do with it, Ollie?
If you have information on one color, you just use that one color.
Yeah. If you had a question that was for this, then you'd have information about just red, right? Because that's the only color there is. If you have a question like this, then you would still have information about one color. It might be red, it might be blue, it might be green, whatever. Okay, whatever you have information about, let's say it's red again. Okay, if you have information about red, then what we're going to do is ignore the rest of the colors. Pretend that the rest of them don't exist. Okay, I've told you a few times now, that's going to happen on Tuesday's test. You will get multiple colors. Don't let it bother you. Don't let it cause you to make a mistake. Pick the color you have information about and go with it. Ollie?
Would there ever be the one question where they give you information on one color, and then they have to figure out the second color?
That's a good question. I wouldn't say yes, I wouldn't say no to that. I can think of a possibility where they might give you information about, let's say, blue, and they ask you to find something, they ask you to determine something about red. So you've got all the different colors, or at least you've got red and blue in the same question. They give you information about blue, they ask you to find something about red. What you know will stay the same is D. Right? D is going to be the same regardless of whether you're dealing with blue light or red light or green light or whatever, right? The distance between the slits isn't changing. So it's conceivable that you could have to use blue light, given all the information for blue light, to solve for the distance between the slits, and then use the distance between the slits and some information about red light to solve for the wavelength of red or something like that.
So they still have to give you information on red, you just find it by itself.
That's right. No, you'd still have to have all the information about one color and then most of the information about the other color. Okay. I can't say that I've seen a question like that before, but I wouldn't say it's out of the realm of possibility. Probably not, because I don't remember in 20 years seeing one like that. But it wouldn't be a ridiculous question. Like it wouldn't be one of those ones that's, you have no hope of doing. Okay. Analyze a color. Get what you need to get from that color, probably D, because that's the thing that wouldn't change between the two colors, and then analyze the other color separately from one another, right? Yep. Yeah, it would actually. L would stay the same as well. So maybe instead of solving for D, you'd be solving for L and then moving it into the next question, whatever, but you're right. I mean, N could be staying the same too, depending upon how they set it up. N could be staying the same. All right. One more thing. We mentioned this yesterday as well. Usually when you see this, let's go back just to the red for a second here. Usually when you see this on the screen, this bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on, you get your diffraction grating down here with a couple of openings or slits in the diffraction grating, and you've got your light source. You've got your light source down here, right? Actually, I should have drawn that red, right? Because we've got red light there. Goes through both openings, diffracts, interferes, produces that pattern. What's the other possibility? Does the light source have to be down here? Where could it be? Could be. Yeah, it could be up here, behind there. But if I have it set up in exactly the same way, except the light source down here, what's going to happen? Well, the light's going to go through these two openings and produce this, right? So what has to be the difference between the diffraction pattern that we had, sorry, not the diffraction, but the diffraction grating that we had versus the diffraction grating we have now? Instead of allowing light to go through, it just reflects it, that's all. You ever look at a CD think it was the other class that I talked about with this. Was it you guys? Yeah, you look at the CD, the little pits in the CD actually form a diffraction grating, but a reflective diffraction grating as opposed to a transmission diffraction grating. You see those rainbows, right? And why do you see the rainbows? Because it's white light that's shining on it and it splits it up. The diffraction grating splits it up. Okay. If it was just a laser like you have in a CD player or a DVD player, um, then you could see an interference pattern, but it would just simply be one color.
Like actually, when I was cooking those nanomold bars,
Yeah.
I was like kind of smiling because like I used a CD when I was cooking. I played it.
Yeah, yeah.
And then
Let's do a little work with what we started yesterday now, this whole concept of photon theory. You remember yesterday we defined photon as a quantum of energy, a little bundle of energy, a particle of light. Prior to the 20th century, we thought that light was a wave. Now, there's people throughout history that thought it was a particle as well, but consensus was prior to the 20th century, prior to about 1905 with Einstein, that light was a wave. In fact, we had evidence to support the wave nature of light, right? Interference, diffraction, polarization, refraction. It's all wave properties that were exhibited by electromagnetic radiation. Peter, you're going to ask me if I watched that video? I haven't. I did yet. I haven't had a chance to watch it yet. I watched about 5 minutes of it, but that's about it. Thank you. I'll have a look at it in the next day or two, though. But in 1905, Einstein came up with this theory that we called photon theory that says, yeah, light is a wave, but it's also a particle at the same time. It has what we call a wave-particle duality. Now, for the next couple of days, we're going to talk, we're not going to say that the wave nature of it doesn't exist. We're just not going to talk about the wave nature of it. We're going to talk about the particle nature of it. The wave nature is still there. We're just going to refer to the particle nature. Yep. So we're saying now that light is a wave, but we're saying light is also a particle called a photon, a little bundle or quantum of energy. A photon's like a little rock, okay, a tiny little pebble with a certain amount of energy. The energy of the rock would be 1/2 mv squared. The energy of the photon would be h times f or hc over lambda. Both of those. And those are both on your data sheet. E stands for energy, F stands for frequency. See that energy is related to the frequency. If you think back to the spectrum, the whole spectrum that we had first day of this unit, right? Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Radio waves were low frequency, low energy, high wavelength. The frequency and energy were directly related to each other by this equation, and inversely related to the wavelength. Now, finally, what's this? What's this thing right here? This H? Yep. Yeah, it's a constant that we call Planck's constant. Einstein was the guy who came up with this photon theory, the idea that light exists as a particle in addition to a wave. But he wasn't the first guy to come up with quantum theory. Quantum theory, the idea that energy is quantized. Quantized means certain levels. Okay? Like walking up a set of stairs. You can have 10 joules on the first step, or 20 joules on the second step, or 30 joules on the third step, nothing in between. That's, in essence, quantum theory. Planck is one of the originators of quantum theory, so he gets a constant named after him. Einstein took his ideas and kind of extended them to light, the idea that light is a particle or a quantum of energy. The value of Planck's constant, by the way, 6.63 times 10 to the minus 34 joule seconds, or we could say 4.14 times 10 to the negative 15 electron volt seconds. Why two different values? Because we get two different units. The speed limit on the highway is 110 kilometers per hour. It's also roughly 30 meters per second. Doesn't mean there's two speed limits, it just means there's two different units that describe that speed limit. All right? Which one do we use? Usually whichever is convenient. Usually whichever is convenient. If we want the energy in joules, we're probably going to use the first one. If we want the energy in electron volts, we're probably going to use the second one. But there are a couple situations, and we'll see those coming up in the next 2 days, of when you must use joules. You must use the 6.63 value. I'll point those out when we get to it. I want to do an example here. on page 706, chapter 14. How much energy is carried by a photon of red light with a wavelength of 600? Let's circle this nanometers because we know we don't want that. This is a really straightforward question. Want to find the energy of this photon? We're going to say hc over lambda. What do you want the energy in, joules or electron volts? Pick one. It doesn't say. Joules, okay. So let's use 6.63 for Planck's constant. Times 10 to the negative 34 joules seconds. Times 3 times 10 to the 8. Divide it by, be careful here, 600 times 10 to the minus 9. When we do this, I think we end up getting 3.315 times 10 to the minus 19 joules. We're going to round that to 3.32 times 10 to the minus 19 joules. How do we get that one so quick without using a calculator? There's always a trick, right? Always a trick. What was the trick here? Yep. Yeah, exactly. That's exactly what I did. 3 divided by 6 is a half, so 6.63 times a half. Really, all I had to do to be able to do in my head was multiply 6.63 times a half, right? And then the exponents just kind of fall into place. Good? Of course, you're fine using your calculator for that, right? And on a test, I would too. I'd use a calculator too on a test. Yeah. Good? All right. Well, the questions that go with this practice problem on page, or example problem on page 706 should be pretty straightforward for us. The next one we'll see is going to be a little bit more challenging. So let's spend a couple minutes at least doing these ones ourselves to see if we can figure it out, and then move on to something a little bit harder here. Question number 1 says, what's the energy of a photon whose frequency is this? This is just E is equal to H times F question. Since we're looking for the energy in joules, we're going to use 6.63 times 10 to the minus 34 joules seconds. Sometimes I skip units, but in these questions, it's a real good idea to include those units because it's going to help us to remember what units our final answer is going to be in, right? So joule seconds, and then the frequency is 4 times 10 to the 14 hertz. When we multiply those two numbers together, we should get 2.65 times 10 to the minus, what do they have here? 10 to the minus 19 joules. Oh, is that okay? Yep, that's it. Now, if you were given the energy instead of the frequency and asked what kind of light is this, what kind of EMR is this, then you would work backwards, solve for the frequency, and then compare it against the bands of frequencies that you memorized back the second day of this unit, right? And you could identify what kind of EMR it was based on that. This would be 4 times 10 to the 14. So this would be barely visible light, right? So that would be straight up red, yeah. All right, let's take a quick look at number 3 as well, just a real quick look. We just want to convert units here, electron volts to joules. And I'll just remind you that 1 electron volt is 1.6 times 10 to the minus 19 joules. 15 electron volts is x joules. So we're solving for x here. X goes up by multiplying. 1.6 goes up by multiplying. X ends up being 15 times 1.6 times 10 to the minus 19, which gives us, I assume the answer in the book is right, 2.4 times 10 to the minus 18 joules. All right. They're asking you to do that conversion, gentlemen, because there are times when we have to use one or the other. Maybe it's a multiple choice question, and we do it in joules, but all the answers are in electron volts. Okay, or it's one of those situations that I told you about that you're going to see in time a little bit later today, gentlemen, where we have a situation where we must use joules, 6.63 value there. Got it? All right, let's do another example here. This one is page 707. This one's a bit trickier. It says your eye can detect as few as 500 photons of light. So that's not a lot of photons, actually, when you think about it. A photon is an energy, usually, if it's visible light, 10 to the minus 19 joules. it only takes 500 of those for you to actually see something. Below that, and of course everyone's different, right? But on average, below that, you don't see anything. Above that, you do. Okay, you see light. The eye is most sensitive to light having a wavelength of 510 nanometers, bless you. What's the minimum amount of light energy that your eye can detect? Well, the amount of energy of one photon of this color of light is HF, or let's say HC over lambda. So what I want to do here is find the energy of one photon, 6.63 times 10 to the minus 34 joules seconds, times 3 times 10 to the 8, divided by 510 times 10 to the minus 9. That's going to give me the energy in joules of a single photon. Let's figure out what that is. 6.63 times 10 to the minus 34. And what do we get? 3.9 times 10 to the minus 19 joules. Okay, the energy of a single photon of this kind of light, the color of light that our eye is most sensitive to. How do you find the energy of 500 of them? Times it by 500. I think when we do that, we're going to get 1.95 times 10 to the minus 17, 16, which is going to round to 3 digits, I guess, yeah. So 1.95 times 10 to the minus 16 joules. If we needed electron volts, well, we had 2 options if we needed electron volts. We could have found the energy of one of them in electron volts using the 4.14 value, or we could have gotten joules like we did and then converted it to electron volts after the fact. Let's have a look at these 3 questions now on page 707 for a couple minutes. Let's have a quick look at number 3 here. How many photons of green light are required to deliver 10 joules of energy? You guys remember back in Unit 2 electricity, we had to find the number of electrons? We said the number of electrons was the total charge divided by the charge of one electron. Remember the analogy we used? We had a bag of apples that weighed 600 grams. Each apple weighs 200 grams. How many apples do we have? 3. The total mass divided by the mass of 1 gave me the number of apples. The total charge divided by the charge of 1 gave me the number of electrons. The total energy in number 3, the total energy divided by the energy of 1 photon will give me the number of photons. So here's what I want to do. I want to find the energy, the total energy, I've already given actually, is 10 joules. I want the energy of a single photon, which I'm going to find by saying E is equal to hc over lambda. So let's do that now. We have our total energy in joules. Let's find the energy of 1 photon in joules. So let's use the value of 6.63 times 10 to the minus 34. Multiply that by 3 times 10 to the 8. Divided by lambda, which is 550 times 10 to the minus 9. Who has the value of energy there? Somebody have that? Or okay, I'll calculate here. What do we got? 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 550 times 10 to the minus 9 gives me, what did I do? Should have just started again. Is that right? Yeah, I think that's right this time. Gives me 3.616 times 10 to the minus 19. So now I can divide the total energy divided by the energy of 1 single photon. And when I do that, I should get 2.8 times 10 to the 19 photons, right? When you're looking for a number, Whatever the context is, when you're looking for a number of something, how many electrons do you have? How many apples do you have or oranges do you have in the bag? How many photons do you have? It's always going to be the total of something. Energy, charge, mass, something. The total divided by the amount for one. Total mass divided by the mass of one. Total charge divided by the charge of one. Total energy, in this case, divided by the energy of one. Good? Okay, let's do one more example here. And I'm not going to give you time to work on these questions right now, but rather I'm going to assign those questions. This says how many photons are emitted each second by a laser pointer that has a power output of 0.4 milliwatts if the average wavelength is 600 nanometers. Whew. Looks a little ugly. Let's write down some givens here, okay? The power output is 0.4 milliwatts, or 0.4 times 10 to the minus 3 watts. The wavelength is 600 times 10 to the minus 9 meters. We're looking for the number of photons. Yep. Joules over T, you mean? Or, no, I see what you mean. Yeah, no, you can, yeah. Power is equal to work over time, which is joules per second, right? And it says, wait a second, it says how many photons are emitted each second? So why don't we say our time is 1 second then, right? That means our work or our energy is 0.4 times 10 to the minus 3 watts times 1 second. We can say 1 second because we're looking for the number of photons per 1 second. Turns out my energy is the same as my power here because my time is 1 second. Okay, there's my total energy. Now, let's get the energy for one photon. It's hc over lambda. 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 600 times 10 to the minus 9. And I think that's going to give me, I think it's going to be 5 times 10 to the minus 19, isn't it? No, it doesn't. 3.315 again. So the last question asked me to find the number of photons. I was given the total energy. I had to divide it by the energy of one photon that I had to calculate. Here I have to calculate the total energy and the energy of one photon and then divide them. So to get the number, it's going to be ET over E1. And when I calculate that, I don't know what it works out to be, but it gives me the number of photons.